So last time we talked about angular momentum, and we talked about all this stuff. So in fact, one thing I feel like I should have said last time to make it clearer, right, is say you have a spinning top, right? I assume you know what a spinning top is, like a little toy, right? Well, when you spin it, right, it has this point. It spins around this axis, right? So even though it spins like this, right, and you could say that if you take any point on it, that it has a velocity that way, like momentum in this direction, right? The angular momentum is down the rod, right? That's the direction of the angular momentum. In this case, we'd say it's that way. Okay, because if the z direction's up that way, if we were looking at it from the bottom from here, we'd see this going. If it's rotating down, then we'd see that going clockwise. So we'd see a negative momentum here. So it would be down rather than up. If it was going up, then it would be spinning that way. Okay, and it was equal to, if you remember, L is R cross P. So R cross the momentum is what we decided. So you could say that for any point on here. And you can also say that the L of all the points is equal to the sum of all of the R cross P's, right? You could take R cross P for every single point of this, and then the sum of all of them is the total angular momentum of the whole system. That's L. Okay, so this is, for J equals 1 up to N, so for every single particle in this thing. Alright, let me shut my window because there's someone drilling outside. Right, so what if we wanted to find how the momentum changes, right? So we've got L is R cross P, but we want dl by dt. Okay, we want the change in momentum. Well, the change in momentum here, if we take the d by dt of this, we use the product rule. So this would be dr by dt p cross p plus, and then we do the other side. So we do differentiate that to cross it with that, differentiate that, cross it with that, like that. Hope you all understand the product rule. Okay, so that's what that's equal to. Well, if you look here, dr by dt is v, right? So this is v cross p. Now, if you cross something with itself, you're going to get 0. Because, for instance, that would imply that you have some axis going straight up, and you have a momentum going straight up in that axis. Well, that's not going to cause an angular momentum, right? Or if we just do ijk, right, and we have v, let's say the v is just in the x direction, and the p is just in the x direction, right? And we're crossing them with each other, so all this is 0. You're gonna get, they're all in the same column, right? And as long as they're in the same column, you're gonna get, you're gonna get 0. So the point is v, remember, p is mv. So this is the same thing as m v cross v, which by definition is 0. Okay, so this whole thing disappears. As usual. It's a common theme in these physics lessons, isn't it? That just large bits disappear. So we're left with just this, right? And we know another name for dp by dt, don't we? And dp by dt is force. The rate of change of, this is Newton's second law, right? The rate of change of momentum is force. Well, now we have the rate of change of angular momentum is r cross force, which is what we call torque. So torque is dl by dt. So this is the same thing as Newton's law, F equals dp by dt, right? Torque is dl by dt, and it uses a tau, the Greek letter tau. Okay. So we can apply torque in different. So when I apply a force, I move something, right? So if I want to move this in the z direction, I apply a force and it moves. Okay. I can apply an x force and I can apply a y force, right? So right now I'm applying forces on this, but I can also apply torques on this, right? Right now there is no, relative to my hand, right, there's no torque on this. Relative to here there is a torque because, it's spinning around this point, right? But say I want to add torques to this. Well, okay, I can add a y torque, which would be like this, spinning the pen round. That's going to be a y torque. I can add an x torque, which would be this, right? This is an x torque. Or I could add a z torque, which is this, right? You see? So so is it making more sense now, this cross product thing, when you think of the angular momentum is in this direction, that's the place that gets stuck and it rotates around that point. So if the angular momentum is going in that direction, then it will be spinning like that, right? If the angular momentum is going in that direction, this is going to be spinning like that, or like that, right? Does that make sense? So when I apply a torque to something, I can accelerate it angularly. I can give it an angular acceleration, which we call alpha. Instead of ma, we have something else, I alpha, which we'll get into in a minute. Right. But in the meantime, let's talk about torque. So remember Newton's second law, we saw that F is dp by dt. Well, we know that if the force is 0, right, that means that dp by dt is 0. Okay. So that means that mdv by dt is 0, and that means there's no change in velocity, right? There's no change in velocity. So therefore, if there's no force, right? Sorry, if there's no force, there's no change in velocity, right? It can't change, right? Well, and that's Newton's first law, right? An object will always stay at the same velocity unless there's a force acting upon it. Well, we can do the same thing here. We can go, okay, well, dl by dt, so the torque, right, equals r cross f, right? Well, if the f is 0, if there's no force on here, that means that r cross f is 0, so dl by dt is 0. So the torque is 0. Right? So therefore, right, you can see here, this is conservation of momentum, because the momentum's always conserved. You can't change momentum if there's no external force. As long as there's no external force, the momentum will always be the same. Well, it's the same here. As long as there's no external force or external torque, same thing, right, in this case, then there's going to be no change in angular momentum. So we can say that angular momentum is conserved at all times. What that means is that, well, this is stupid, I've done it in the middle of it. If I give you these lecture notes, they're going to be annoying. If the torque, okay, angular momentum is always conserved, so well, first of all, let me just quickly talk about torque in a system. if we have a system with lots of little particles in it, and each one of them has their own, momentum going in all sorts of different ways. Okay, well, we're only interested in the momentum, this way, around the circle, whether it's going that way or that way, right? These things, they all have an R and they all have a P. And we can say that the L, right, is equal to the sum of R cross MV, right? Because each one of these each little momentum is R cross P, and the total momentum is the sum of all of the little momentums, right? Well, if we do dl by dt, so we differentiate the momentum of the whole system, then we're gonna get, if we do dr by dt is v, right? Cross of mv plus r cross m, and then dv by dt, right? So to be clear, oh my god, we differentiated this side. This is here. We differentiated this and left this alone. Now we're differentiating this and leaving this alone. So we've got r cross m. If you differentiate v, you get a. You get the acceleration. Differentiate velocity, you get acceleration. So this thing is 0 because if you cross v with itself, you get 0. So we can see that the dl by dt, right, is the same as the sum of all the r cross MAs, and MA is force, right? F equals MA. So we get the sum of all the RFs, and RF is torque. So we get the sum of the torques. So in other words, the torque of the whole system is the sum of all the torques. It's the same thing, they all add up. So if you take this torque, add it to this torque, add it to this torque, add it to this torque, add it to... So if if you've got a rigid body and it's got several children, right, and you want to figure out how this thing's going to rotate, well, you find the rotation point. So say you're rotating around the origin, you find the distance of each one from the origin and multiply it by the force on each one, and that will give you the torque of the entire system. And then you can do it the other way around to add torques to everything, right? But typically in Unity, you just use r.add torque to add your torques. So that's the same as r.add force, right? You can give your thing. So much like in a rigid body, it hides the acceleration from you. You don't see that. You can only work with adding on to, well, the acceleration's every frame. So you can only add forces and then it resolves them in a frame, or you can, add, you can do velocity plus equals, right? That's the same thing as an acceleration. Well, you can do the same here. You can add on to your angular velocity, or you can use add torque, right? And that will change the angle. So the torque changes the omega, changes the angle, and the acceleration changes the velocity, changes the distance, right? They're all analogous. The thing is, the two systems, once you've learned one, you kind of know everything, right? It works the exact same. Well, we can even see all of Newton's laws are the same. So let's look at Newton's laws. We know that Newton's first law is that, let's say, an object will remain, this is not exactly how it's written, at a constant velocity unless compelled by an external force, right? We can say that 2 is the second law, right? Second law is that F equals dp by dt. And Newton's third law is that for every force, there is an opposite force of equal magnitude. Right, so now let's rewrite these for rotation. Okay, so an object will remain at a constant angular velocity. Oh my god. Whoa, I got rid of it. Angular. No, I didn't. Go away. What have I. Okay. A force will remain at a constant angular velocity unless compelled by an external torque. F equals dp by dt. Tau equals dl by dt. Okay? For every force, there is an opposite force of equal magnitude. For every torque, there is an opposite torque of equal magnitude. Okay? So actually what this means is if you have so let's say you walk on the earth, right? And it's spinning, this way. Right? And you walk around the earth, so you're standing here at the equator, right? And you foolishly start walking east, right? So you start walking that way. Well, if you walk this way around the earth, you add an equal and opposite torque in the opposite direction. So if you drove round and round Earth over and over again in this direction, right, you would steal the Earth's angular momentum. If all of humanity kept walking round and round and round Earth, driving round and round Earth the wrong way, like east on the equator, we would slow down the Earth. Luckily, not by that much. But if from now on till the end of humanity, all our planes decided to fly east, we would actually be slowing down the Earth, and then that would be pretty bad because then days and nights would stop, and the magnetosphere would stop, and we'd get bombarded by rays, and it would be bad times essentially, and there'd be problems with the moon as well. So you can actually, when you jump up in the air, right? When you jump up on the Earth, you fall back down again, right? So even though you do push the Earth down, you come back up. But when you walk east and you don't come back, you actually permanently rob the world of angular momentum forever. Well, unless you go home again. If you go home again, it's fine. But that's how you walk. When you walk with friction, right? And that... In fact, I believe it was Pharrell. Do you remember Get Lucky, Daft Punk? And he says, what keeps the planet spinning? Conservation of angular momentum. I believe that was a lyric. But if you go into... he says the force from the beginning, right? Which is technically not... It's more like the torque from the beginning. Yeah, he's right. Pharrell's right. The reason the Earth's still spinning is because we're not robbing it of torque right now, but we can. An example of this in Unity. Do I have Unity open or not? Yeah, I do. Okay. Luckily, here's one I made earlier. Right, see this thing? We're adding torque to it. Right, so we're adding a negative torque. And remember, because we're in a left-handed system, if we add a negative torque, that means it's going to rotate clockwise. Right, so you're just going to get used to that fact in Unity. Minus angular velocity makes clockwise rotation, because k is forward, right? So if you have your thing going out, and it rotates that way, right? So that way, then that means that k is backwards. So it's negative angular rotation. So that's the joy of... I think in general a left-handed system is good, but this is the only place where it's not cool, is that clockwise rotation becomes negative. But anyway, so we're going to do this. and we're just gonna, first of all, we're gonna rotate it in space. Okay, no gravity, just rotate it in space. Okay, you see it spinning, you see it accelerating, right? Because we're not adding an angular velocity, we're accelerating it. If you see the coin attached to it, it's getting faster and faster. Right? So, now what we're gonna do, well actually, we'll let it accelerate, and then we'll add some gravity to it. And watch what happens. Nothing, right? It just spins. The reason it spins is because currently we have a material called frictionless, right? Well, what if we take frictionless and we add some friction to it? It really didn't like that. I suppose you're not supposed to do that mid-calculation. Let's undo that. Well, I've made another one before. It's called high torque, right? Let's add high torque to here. Look at that. You can understand what's going on here, right? As soon as I add friction to this thing, right, and I add some gravity to it, because, you know, F is mu r. Remember that? Right? So the frictional force, you've got your ball, right? And it experiences, it's pushing on this, right? And you've got the friction of this rotation, right, going this way. So the ball's going to end up going this way as it turns. You're going to get the torque's going to impart on the thing mu r, where this is r, which is mg. So mu mg this way, right? And that's going to accelerate in this direction, right? Because of Newton's second law, but for torques. So you're saying? Okay. So we've got that. So now let's look at let me check that none of my links are important to this part of the lecture before I move on. No, they're not. Okay. Right. So now we have these quantities. We're almost finishing our rotational motion, right? We know that P. Well, okay. This is translational, right? This is the physics we're used to. We know that F is dP by dt, right? Which is ma as long as m's constant. We know that P is mv. Okay. We know that dv by dt is a. We know that dr or ds by dt is v. We know the kinetic energy is half mv squared. And we know that the work is Fd. Okay? And there's also another thing. I never taught you this, but power is force times velocity. We don't really use power. It's more of a measurement. It's a bit of a stupid measurement when you think about it. But the good thing about power is it's joules per second, right? Wait, no, a joule. Sorry, joules are power per second, right? It's, if you see Fd, it's the same as Fd by dt. It's the work over time. So this is energy, right? So it's oh yeah, it's energy over time, right? Yeah, so a power is telling you how much energy you produce in like a second, right? It's a measure of your energy production. Anyway, so we don't really use that, but just in case you need to know that, whenever you see like kilowatt hours, that's why, because that's your power, right? And kilowatts is the actual kilowatts is the Oh no, power. Okay. Kilowatts is your power. What is the unit of power, right? And kilowatt hours are how much energy you produce because you times it by the time. So if you multiply energy by time, you get power. So therefore, and power is, sorry, energy is d power by d time. Right. Anyway. So that's why sometimes you see, if you see solar panels are quoted in kilowatts instead of kilowatt hours, you should, kilowatt hours instead of, well, basically the energy industry gets confused about what is a watt and what is a kilowatt, what is a watt and what is a joule. They really don't seem to get it. So if you ever read about solar panels, it's probably nonsense. It's marketing mumbo jumbo. Because they want to use the big numbers, right? And most people don't understand the difference between work and power. Anyway, rotational. That's beside the point because you're not going to use it in a game engine, so whatever. Rotational. We have torque, right, is equal to dl by dt, and torque, right, so L, right, we need this quantity. It's going to be something times omega, right? And then we've got d omega by dt. We're going to call that alpha. That's our angular acceleration. And we can say that our d angle by dt is omega. Remember we said this before. And our energy, we also said the energy is... actually, I don't think we did say the energy, but... whatever. We're going to talk about, instead of mass, now, we don't use mass here, we use inertia. Okay? So this is I alpha. We can also say that the rotational work is the torque times the angle. So it's the same as, well, we could have called this Fs, right? To make that clearer that this is the same as this. Right, so you see it's all the same thing. I'm sure you can guess what the energy is. The energy rotational is half I omega squared. Right? And the power, see if you can guess this one, torque omega. Right? It's all the same thing. But what is I? Okay, so it's called the moment of inertia. Now you know that mass is something's ability to resist acceleration. So if something's heavy, if something has a lot of mass, it's hard to push it. Well, if something has a lot of inertia, it's hard to turn it. So say if something has low inertia, it's going to be easy to spin like this, right? It's going to be really, really spinnable. But if this had a high moment of inertia, it would be like this. Okay, that's what inertia is. Moments of inertia, right? Moments of inertia rather than just plain old inertia, because mass is inertia, right? But that's why it's called inertial mass. Inertia is your ability to resist acceleration. The moment of inertia, the moment of inertia is something's ability to resist angular acceleration, which is also known as moments. Let's talk about what I is and how we get it. You're never actually going to need this probably, unless you're writing your own engine. But like, I'm going to teach you anyway. It's not that long. It's a bit mathsy, but if you want to zone out because you don't care about maths, and feel free. You might learn something even if you don't care. Right. So this time we're making a spinning top, and we're saying that this is X, so this is I. This time we're saying this is Y, right? So this is J. So it's like paper on a table. This is X and Y, and this one's Z, and we're saying K is up. Okay. So the angular momentum is along this axis. So we have a spinning top, right? Like that. And the spinning top, okay, it's going to get a bit confusing here because we said L equals R cross P, but I'm going to change that around the names. Just the names. The maths is still the same, but we're just naming something different. Because I'm going to call this thing R now, the radius of this circle, of the top. Okay? Now, remember that when we talk about L equals R cross P, we're talking about the distance from the pivot, right? We're talking about the torque around the origin. So in this case, when we say R cross P, we mean this line, not this line. So for now, I've called this R. So we need a new name for this quantity. We're going to call it D, the distance, right? That's the distance from our origin. So actually here, it's not L is R cross P. It's L equals D cross P. And the reason I've done that is that if we think about this thing, right, it's spinning, we'll say it's spinning this way, omega, right? So it has some P this way. Okay. Remember that we can find that the P is going to be mv, and we remember that v equals r omega. Well, when we're talking about v equals r omega, we're talking about this r. We're talking about the distance to the axis. We're not talking about the distance to the origin. We're talking about the distance to the axis you're rotating around. So the reason I'm using r here and d here is because d is the distance from the origin to the particle that's rotating, and r is the distance from the axis. Hope that's clear. Alright. And so we have some omega, because this thing's spinning clockwise. Right? It's spinning clockwise, but if you imagine we looked at it from the bottom, so if this is our screen here, and we're sitting here, this is our head. Here's our ears. Right, that's the top of our head, and our eyes are here. Right? And we're looking through our screen. Then we'll see the bottom of this. So we're going to see K forward. Even though this is rotating clockwise here, for us, it's going to be rotating, the top's going to be moving left. So it's going to be rotating anti-clockwise. Do you see that? Like, if we're in the Unity camera view, right, this is the camera, and it's going there, right, this is us sitting at our monitor, this is Unity, and we're looking up at this situation, then even though right now where we're looking at this, the top appears to be spinning clockwise, when we're on the top side of it, when we're on the bottom side of it, it will be going anti-clockwise, because we're going to see this as the top, and this top point's moving left. Now from our view, the top point's going to be moving left, right, so it's going to be going anti-clockwise. Okay? So a positive L is making an anti-clockwise rotation. Alright. Anyway, so let's get rid of us. The important thing is, oh my god, whoa. That's weird. I didn't know I could do that. Right. Anyway, so we can say that L equals D cross P. Right? Because it's the normal formula, L equals R cross P, but instead this time we're using D as that, right? And we can say that P is mv. We know that, right? Momentum is mass times velocity. So L is m, oh my god. L is m times D cross V. We pulled the m out because it's constant, and then we got the same thing except the P has become mv, right? So L is m D cross V. Now the thing is, we're only interested in the angular momentum vertically, and we're only interested in this rotation. So if you think about a spinning top, one thing you might notice is that when you... Oh, I can maybe actually... Actually, no, there's no way I'm going to be able to hold this and spin it at the same time. Okay. Yeah, I can't spin it fast enough. If you it has too high of a moment of inertia, that's the problem. So if you look at your spinning top... Oh, look at this line I've drawn. That's interesting. Okay. If you imagine a spinning top, what happens is you spin it off, and then it makes a torque on the table, and that makes it wobble, because when it experiences a reaction torque, it's going to end up tilting like this way and this way. And so, when you see a gyroscope spin like this, like this. Do you know what I mean? It wobbles in a circle like that, right? It doesn't just go in a straight line, it goes round and round. That's called gyroscopic precession. But we're not interested in that right now. The only thing we're interested in is the absolute vertical momentum. We're not interested in the momentum in that direction, because as the top spins, it's going to go in these different directions. But we're just trying to simplify, so we're just interested in the upwards direction. So to get our upwards direction, K, you know, the K direction, because it's in Z, we can do K dot L. Okay? If we dot the K, if we dot the Z axis with L, then we're just going to get the upwards momentum, which is the only stuff we care about right now. So if we do that, we're going to get MK dot D cross V. Now here's some maths that is just true. A dot B cross C equals A cross B dot C. It's just true. You can go if you don't believe me, go and work it out yourself. It's not that tough, but it's that's just a fact of life, right? So we can say the same thing here. K dot L is equal to M K cross D dot V. Okay? So the upwards momentum in the upwards direction is equal to M K cross D dot V. Now here's where the maths gets a bit annoying. Not too annoying, I'll try and explain you through it, but it's a bit annoying. The cross product, right? A cross B, if we just want the scalar of it, we get AB sine theta. So let's look at this triangle here, right? This is our theta. Okay. In this case, we have D. We're doing K cross D, right? K is just this upwards direction. It's not all the way. It's just one long, so it's up to there, right? So if we do, okay, the point is K has a length of 1. So K times D, this KD sine theta is the same as D sine theta, because K is just 1. It's 1 times D times sine theta. So if we want D sine theta, remember that this line up here, the height of this thing is D cos theta, and this R radius is D sine theta. Okay? Because it's away. The same side as cos, the away is sine. So this line is D sine theta. So essentially, you can see on this diagram that that's the same as R. Right? So D sine theta is R. So K times D, K cross D is R. Right? But that is only the magnitude of it. Right. So I'm going to erase all this now because it's in the way. Right. But the magnitude of this thing is R, this line here. So it's the distance from the axis, right? The horizontal distance from the axis, right? Now we need the direction of it. Okay, well, we can do the direction just by doing the hand rule thing. So let's look. We have K. Okay, so K is straight up. So we put our hand straight up, right? And then we're going to curl it in the direction of D. Well, D is that way. So we curl down, right? So we curl our fingers down this way, right? Then our thumb's going to be sticking out here, isn't it? Right? So this thumb is the direction of K cross D. Right? So the magnitude is R and the direction is this way, which happens to be the direction of the rotation. Have you noticed? We can call that that. right? So, again, I'm going to scribble this out. This thing, this vector, and I know that was complicated, but sorry, this thing is the same as r times that vector, right? Well, the v is in that direction. If you notice this p, right, the p is going that way, and v is going that way. That's also going in theta, right? So we're dotting that with v, right? Well, if you dot something in the same direction, then it's just 1. If you have if I have this vector and I dot it, and this is x, and then I have this vector and it's y, and they're going in the same direction, then x dot y equals x times y, right? So, except, it's scalar. So that whole thing is just RV, right? This whole thing becomes MRV. So K dot L equals MRV, right? Now, remember that V equals R omega, right? So this V is the same as M R omega, so M R squared omega. Right, so we can say that our L, the L that we're interested in about, so the L in this direction is MR squared omega, which equals I omega. Congratulations, we've found inertia. This is inertia. MR squared. If we have some point, I know that maths is annoying, but you'll never have to do it again, don't worry. The inertia of this thing is just the okay, so in general, the mass is just the mass, right? And F equals ma. Well, the inertia is m times r squared, and the torque is I alpha. So the torque is mr squared alpha. Okay? So what that implies is that the larger the mass is from you, the harder it is to rotate something. So if you have the exact same object, like an oar or a baseball bat, right? And it looks like this, right? All the mass is up here in a baseball bat, right? This might be, especially if you've got this bit's plastic and this bit's metal, right? Then most of the mass in this thing is up here. If you spin it from here, it's actually harder to spin than if you flip it the other way and spin it. If you spin it from this side, it's easier. Or if you take a giant oar, you take a big old oar, and you spin it from this side where most of the mass is, it's easier to spin than from this side. Now, this may actually seem counterintuitive, because if you know that if you press a door, it's harder to open it. If the door hinges here, it's harder to push the door open from this point than it is from this point. But that's because here you get higher torque. Your torque is F times your distance. So the further you are away from the door, the easier it is to push it. However, if the mass of the door was not the same, if the mass of the door was constant, you had a heavy bit on the door here, you had some giant hunk of iron in this bit of the door, then that would actually, regardless of where you're pushing it, that would be harder. Well, I mean, yeah, that would be harder for you to rotate around this axis than if this mass was here. Okay? So you can actually, and the how it works is the momentum, you can sum it. So say here you've got some game object that's got various masses attached to it, and you want to work out how hard it is to rotate. And these are at 3 different distances: R1, R2, R3. Well, the total momentum of this system, I, equals m1r1 plus m2r2 plus m3r3. Oh, squared. Right? So you just sum all of the inertias, and that finds you the total inertia. So L is I omega. That's another fun thing. Right, so your momentum is equal to your inertia times by that. Somewhere that comes up is, let's say you have a ball, right? A ball is made up of loads of tiny little points that don't move, right? So when you do a ball, you need to check the inertia of every single point in the ball. And to do that, you need to do a triple integration. We are not going to do a triple integration because no one wants to do that. It's boring and it's annoying. In fact, I'll show you the solution for a sphere. You want to do that? No, I didn't think so. You don't want to do this calculation, right? But all they do is they integrate this. They make a disk, right? And then they slice it into big chunks, and then that gives them the inertia of the whole sphere. But you can see that the moment of inertia of different things are different. So a point, like in unity, we use point masses. All the masses in one point, and that's mr squared, right? But if you have a solid disk, it has this inertia. This is the inertia of a sphere. This is the inertia of a rod. And you can calculate this by summing the inertias of all the points. Well, what does this mean? What does it mean to you? Well, look. Here's some things rolling. You see this second one was the yellow one was a solid sphere. The solid sphere moves faster than all of the rest of it, and the hollow cylinder moves less fast. That's because the hollow cylinder has a higher moment of inertia, and the sphere has a lower moment of inertia. So even though they all have the same mass and they all have the same radius, the solid sphere, this is a hollow sphere here. This is a solid cylinder. You see, solid things roll faster than hollow things, and spheres roll faster than cylinders. Right, and it's nothing to do with the friction, because this is frictionless, this surface. This is like ice. So, if you see, right, here, we can see we can look at the hollow sphere. Right, this is the thin, gravity's pulling it down. Well, if it's completely frictionless, well, let me think about that. Would it roll? It would. Yeah, because there's gravity. Oh, it would slide, wouldn't it? Yeah, it would just slide. Yeah, you're right. There's going to be friction. But it's not the. It's the same. Okay, I know that this. Yeah, you're right. You're right. They do need that. Kind of is what I said before in Unity, right? But the point is that it's not. The cylinder isn't rolling slower because there's more friction. Because obviously there is more friction on the cylinder because it's all the way across, right? There's much more surface area than on the sphere where there's only one small point touching the slope. But the reason they're going down is not because... In fact, you'd think with more friction that it might get more traction, right? But no, it's all based on this, right? This thing... You see that this is 2/3, 0.66. This is 0.4. So this has a lower moment of inertia, so it rolls easier. This has a higher moment of inertia, so it rolls harder. There's another little animation on here. That's one of them. Oh look, these are just, it's different cylinders where they just change the I. Right? And they roll at different rates. Oh, and one other thing you can do is this. You can actually prove this to yourself right now. I have to take my headphones off for this, so I can't hear you during this, and I don't have much space to do this, right? But you might have done this at some point in your life. I used to do this all the time as a kid because I'm a little weirdo, right? But if you spin on your chair, right, you have a high moment of inertia when your hands are out. You have a low moment of inertia when you're compressed in. So if you spin on your chair and then pull yourself in, you add the angular momentum's the same and it's conserved, but because you pull in, right, you actually because the angular momentum's conserved, but the inertia's gone down. It's like changing the mass, right? If you throw something and then it somehow gets lighter, it would get faster because the momentum's conserved. So right, I'm gonna spin myself, right, and then I'm gonna pull up, and you end up I've not got enough space to actually properly show this, but you should spin and then you'll gain. If you pull back, you'll see yourself suddenly accelerating. I don't know if you can see it. Wait, out, in, especially at these slower times. In, out. Okay, that's the best demonstration, right? I can show you right now because I spin myself really slowly. Right. As soon as I spread myself out, I slowed down because my moment of inertia got bigger, and it will actually square, right? Like if you because it's squared, if I'm spinning something like a rod, right? Sorry. Let's say I have a pipe here. Or like a really thin pipe, okay, like this, right? And I have a string going down it, and I have a ball on the string, right? And it has some omega, and it has some r. Well, if I pull the string down, so the ball moves to here. So before it was moving in a circle like this, and now it's moving in a circle like this. It's actually now going to rotate at 4 omega because I've halved r, right? So before I had, my I was mr squared. Well, now my new I is m r over 2 squared, which is mr squared over 4. So my mass is, essentially my inertia's quartered, so my angular velocity will quadruple. So, if you pull in that, it's actually going to quadruple in speed if you pull the string in halfway. Right? Yeah. And the thing is, in Unity you can't specify inertia like you can with mass. It calculates the inertia itself. So I'm pretty sure, I've not tested this, but I'm pretty sure it uses, maybe for a sphere it'll actually assume it's a solid sphere, but in general it uses point masses, right? So if you've got a game object here, it will assume that all the mass is in this point and all the mass is in this point, which makes things easier because you don't have to worry about those annoying formulas. It's just mr squared. So how Unity will calculate inertia is like that, right? And it will. So if you start rotating something around here, it will look at how far it is from there and use that as the inertia. So that's some hidden variable in the calculation. So when you add a torque, you're going to do your torque is I alpha, right? And alpha is d omega by dt, right? So what Unity will do is it will say, okay, torque is I alpha. It will calculate this itself. So all of these are hidden variables that you can't touch. So you add a torque, it's gonna calculate the m and the r squared itself and use that. It's gonna do the tau that you give it divided by the mr squared will give it the alpha that it uses, and then the alpha is the d omega by dt. So then it will do, okay, well, omega plus equals alpha times fixed out of time, right? And so, so your omega, how Unity, if you add torque, if you do this function add torque, what you're essentially telling Unity to do is go omega plus equals plus equals the torque you gave it over mr squared times fixed out of time. And then obviously it will then add this to the angle. So it will do angle plus equals omega, right, in radians. Right, so I don't know if it stores in radians actually. Maybe it stores in degrees. Well, actually, it doesn't store in degrees or radians. It stores in quaternions. But it will do some calculation for the to turn it back into the quaternion. But in general, like in terms of what it's actually going to do, it's going to do the angle in radians, right, plus equals omega dt. So it's it's t over mr squared dt squared, right? And well, obviously it'll use the one from last frame. It's not going to use this one this frame. It's that's a 2 frames later it will do this. Right. So yeah, that's how rotation works. We've pretty much done it. You can look at that yourself. Yeah. Oh, there's also angular drag, right? But angular drag, you can guess how angular drag works, right? It's the same thing. Like a unity drag is really just a lerp to 0, right? So an angular drag is just this lerping, right? So a drag lerp v to 0. An angular drag is lerp omega to 0. So if your force is, minus bv for drag, then your angular drag, so your torque is tau, your angular torque is going to be some, we could call it beta times omega. Right? Which actually, funnily enough, that if you remember when we did the simple harmonic oscillator, we did use betas and gammas. And I believe that was that term. The damping term, we did call it beta. We called A the or a big alpha the amplitude, and then big beta the drag factor. Well, maybe not. Anyway, you get the point. So there we go. We've covered rotation. We've nailed it. We've put a hole in that coffin. We never have to worry about this ever again. Okay. The main takeaways from this in terms of you, because you don't have to worry about inertia, are this sheet. If you're going to know anything, know all this. Again, in a game engine, you're not really worried about energy. You're definitely not worried about power. You're not really worried about work. But you are definitely worried about torque. You're not really worried about momentum, but you can get it during collisions. You can get the collision velocity and stuff like that. So you can multiply that by the mass to tell how hard something smashed into another thing. We're very interested in these ones. Angles, so the angle in radians, the omega. So the really important thing, in case I didn't make it clear, the past couple of weeks, is that omega is how many radians you turn over time. Alright. Oh, we've run out of space on the camera. Oh well. Omega is how many rads you move in a fixed out of time. And yeah, but I think we pretty much smashed through that topic now.